Yeah, fine. So far we discussed about RE model and the analysis of various AC circuits, AC amplifier circuits using RE model, right? So today let us look at the second model, okay, um, which is called as the H model. Okay, fine. So this is your second transistor model. Okay. So this H model is also called as hybrid model. So in short, H model. Okay. So this H model is on the basis of, once again, two-port network parameters. Okay. So what we have to do in case of two-port system is that you need to identify two independent variables. And two dependent variables. Okay, so the two independent variables and the two dependent variables could be either voltage or current. Okay, so for the input port, you have input voltage and input current, and for the output port, you will have output voltage and output current. All right. Now you can choose, two voltages as independent variables and two currents as dependent variables, and vice versa. Okay, so that means to say, you can have different permutation and combination while choosing independent and dependent variables. Okay, now for transistor, or to be specific, for transistor modeling, okay, what we do is we take input current II and output voltage V0 as independent variables. Okay, in short, let me write variable. Okay, for transistor modeling, we take input current and output voltage as independent variables. So that means to say input voltage and output current are dependent variables. Okay, so that is the first assumption what we do while carrying on the hybrid model. All right, fine. Now what we let's look at the two-port system. Okay. So this is a general block diagram of a typical two-port system. Okay, more of it you will study in a network analysis. But what I will do over here is that let me just give you a brief introduction about two-port system on the basis of transistor modeling. Okay, so this is your two-port system. Okay, as I said in the beginning, it will have an input port. So this is your input port, PORT, and it will also have an output port. Okay, so basically this is your black box. Okay, as of now we do not know what are the elements of this black box. Okay, so in electrical engineering, your black box may be consisting of parameters of let's say transmission lines or impedance details of a network, or it could be even components of equivalent circuit of a transistor. Okay, so what we are going to do is, we basically go for the third one, right? Components of the equivalent circuit of our transistors. Okay, all right. So now let us mark the variables. Okay, so input port, okay, you will have input voltage and an inward input current. All right. On the output side, you will have output voltage V0 and an inward output current I0. Yeah, that's what I was talking about in the beginning. So there are 4 variables basically here, right? Input current, input voltage, output current, output voltage. Out of 4 variables for transistor modeling, we have chosen input current and output voltage as independent variable, and input voltage and output current we have selected as dependent variables. Okay. Now that we have described the different voltages and currents, we can try building the relationship between these 4 variables. Okay, between these 4 variables. Okay, so what we will do is, as I said in the beginning, I'm taking Vi and I0 as dependent variable. All right, so let us express Vi, okay, as a function of the independent variable, that is Ii and the output voltage V0. Similarly, I0, let us again express, okay, let's say this is the first function and this is your second function. So I0, let us express in the form of, function of, say, Ii and V0. Okay, let's call this as equation 1. Let's call this as equation 2. Okay, so what I've done is I have just expressed, Vi as a function of, Ii and V0, and I0 I have taken as a function, okay, expressed in the form of Ii and V0. All right, fine. So since we are talking about, electrical system, okay, electronics, yeah, of course, for even electronic system, in the linear region, you can apply the Kirchhoff's voltage law as well as Kirchhoff's current law, right? So this Vi basically, talks about Kirchhoff's voltage law, KVL, and this I0, basically talks about Kirchhoff's current law, that is KCL. Okay, so Vi, okay, let's write it as something like Vi is equal to, okay, linear algebraic equation, let us write. Vi is equal to some unknown H11 and the independent variable Ii plus some unknown H12 and the independent variable V0. Let's take it as 3. Okay, this is how we write the linear, equations, right? Similarly, output current I0, let us write it as some unknown H21 into independent variable Ii plus some unknown H22 into the independent variable V0. Okay. So what I've done is I have taken, a pair of linear algebraic equation, okay, which talks about the input voltage and the output current. All right. Fine. Now, if you look at equation 3 and equation 4, you observe that equation 3 is consisting of a product associated with current and also a product associated with voltage. Similarly, equation 4 is consisting of a product which is in turn, composed of current factor as well as voltage factor. So basically, in your equations, both currents as well as voltages are present. Okay, so it is kind of, mixed terms are present. That's the reason, this particular model is called as hybrid model. Hybrid means mix, right? So your equations will have, voltages as well as current. It's a mixture, right, of voltage and current. Hence, it is called as hybrid model. In short, H model. All right, fine. Now, while writing down the parameters, right? So what I will do, I can even construct a matrix out of it, right? So Vi and I naught, let me put it in column matrix. So let's say this is Vi and this is I naught. Okay, is equal to, what I will do, the independent variables, let me keep it aside. So if I do that, what I get is I'm going to get a square matrix, okay, which is consisting of only the H parameters. We do not know what are they, don't worry, we will eventually, we are going to find out, okay. And the column matrix, which is II and V naught. Okay, so this square matrix, so say, okay, it is basically a 2 cross 2 matrix. Okay, so this square matrix is called as, H matrix or the hybrid matrix, because the elements of H are nothing but, different combinations of H, 1 1 1 2 2 1 and 2. Okay, so this is called as hybrid parameter matrix. Okay, so our aim is to find, what is H11, so on and so forth. Okay, so what we will do is to find H parameters. Okay, let us apply the extreme 2 cases in electricity. Okay, that is open circuit and short circuit. Okay, so what we will do is, first let us say we will short circuit the voltage source. Okay, so let us do something like set, short circuit the output port. Okay, set V naught is equal to 0. That means to say short circuit output port. Okay, so we are trying to, force one of the variable as 0, so that, you will be able to take out the ratio. So set V naught is equal to 0. Okay, in equation 3 and 4. So when you force V naught is equal to 0, okay, that is by creating a short circuit across the output port, what do you get? You get Vi is equal to H11 into II, and the second term becomes 0. So you get from equation 3 as Vi is equal to H11 into II, and from equation 4 you get I naught is equal to H21 into II, right? I naught is equal to H21 into II. Okay, so that implies H11 is basically voltage by current ratio. Okay, on the other hand, H21 is basically output current to input current ratio. Okay, so H11 is Vi by II, right, under the assumption that V naught is equal to 0. Similarly, H21 is being calculated by taking out the ratio output current to input current under the assumption that output port is short circuited. Okay, so voltage by current, what is it basically? Voltage by current. Voltage by current is basically impedance, right? So Vi by II basically gives input impedance. We call it as HI. Okay, so I stands for input. Okay, so the first parameter is H11. Okay, and unit of H11 is ohm because it is voltage by current ratio. Hence, we take this particular input impedance as HI. Okay, on the other hand, I naught by II, okay, is your conventional gain, right? Always we find gain as some output parameter divided by some input parameter. So H21 follows that particular relation, that is output parameter divided by input parameter. So I naught by II is taken as, sorry, forward current gain. Okay. Since it is called as forward current gain, hence it is written as HF. Okay. HF. And in the previous case, right, I have told you that input impedance is taken as HI. That's because, you know, I term is present over here. Okay. So that is what you get when you set your output port as 0. Now, let us set I naught is equal to 0. Okay. That is open circuit output port. So when you open circuit output port, current becomes 0. So when you do that, what do you get? The equations. So I'm sorry, yeah, setting the this II, right? Okay. So it is you are open circuiting the input port. I'm sorry, because you're dealing with the handling of independent variables. So now you set II is equal to 0. So when you set input current is equal to 0, okay, equations are here. So H11 and H21 terms, they become 0. Hence you will be left with Vi is equal to H12 into V0, and I naught is equal to H22 into V0. Okay, so let's write from equation 3 we have Vi is equal to H12 into V0, and I naught is equal to H22 into I naught. Okay. Or hybrid parameter H12 is equal to Vi by V0 under the assumption that input port is open circuited. Similarly, hybrid parameter H22 is basically this is V0. H22 is basically I naught divided by V0 under the assumption that II is equal to 0. Okay. Now, if you look at H12, what is it? H12. It is the voltage ratio, right? But it is not the conventional voltage ratio, right? Conventional voltage ratio is always the output voltage to the input voltage, whereas H12 gives ratio of input voltage to output voltage. That's the reason this particular voltage ratio is called as reverse voltage ratio. Okay, since the term reverse is coming into picture, this particular hybrid parameter is taken as HR. So R for reverse. All right. On the other hand, if you look at H22 expression, what is it? Current by voltage. So current by voltage is basically admittance, right? And the variables, if you see, both are output variables. Hence, I naught by V naught is called as output admittance. Since it is output admittance, hence the corresponding H parameter is taken as HO. So unit of HO is Siemens or Mohs, okay, because current by voltage. Okay, so these are the 4 hybrid parameters, okay, of a transistor network. So what I will do, I will complete the network here. Okay, I had H11 here. So H11 is HI, H12 is HR, and then H21. Okay, what is H21? Is HF. Okay, and H22 is your HO. Okay, if you observe carefully, unit of HI is ohm and unit of H0 is Siemens or moles. On the other hand, HR and HF, okay, I'll just write star. So unitless, they are unitless or dimensionless. Okay, so therefore, H parameter equations can be written as Vi is equal to H11, that is Hi into Ii plus HR into V0. Similarly, I0 is equal to H21, so that is HF into Ii plus HO into V0. Okay, so you have two equations. Okay, so let's name these equations as 3, 4 is done, right? Equation 5 and equation 6. Okay. So equation 5, if you look at, it is something like voltage is equal to current into HI and voltage into HR. So equation 5 is basically KVL equation. On the other hand, if you look at I0, I0 is some HF into II and some H0 into V0. So this is basically your KCL. Okay, so equation 5 is KVL and equation 6 is KCL. Now what you have to do is you have to construct an equivalent circuit by making use of these two equations. Okay, let's see how exactly we do it. Okay, so Vi is the source, right? So what we will do, we will take Vi on the left hand side, plus minus we will take. So what is Vi? Vi is the cause basically. Okay, and these two are sum of effects, right? That is voltage is equal to current into impedance plus HR into V0. Okay, HR is dimensionless. Okay, right? I have already told HR star I have put. They are unitless. So you are just multiplying some unitless number with V0. So again, this product becomes voltage. Okay. So let's do that. So HI into II. So what is the unit of HI? Is ohm, right? So basically ohm into current. So that is actually your voltage drop. So what we will do, we can represent HI as resistance. Okay, and through HI, let us show the input current II. Okay, so we are done with the first term. Okay, the second term, what is it basically? HR into V0. So it is some constant times voltage. So constant times voltage term, okay, in circuits basically represents a dependent source. So which type of dependent source it is? It is a dependent voltage source because voltage is present. So it's a dependent voltage source, hence let us show it with a diamond symbol. Okay, and let's write down the source representation as HR into V0. Okay, so that's your input part of the equivalent circuit. Okay, now let us come to the output part. Okay, so output current I0. So what we will do, we will first mark I0. Okay. So this I0 is composed of how many components? Two components, first component and second component. So basically, it is I naught is equal to sum of first component and sum of second component. That is what you are supposed to do. Okay. Now, if you look at the first component, what do you get? You have HF into II. As I have already told you, HF, see star mark, it is unitless. So basically, you're multiplying and dimensionless entity with the current. So basically, it is some dimensionless gain into current. So this represents a controlled current source. A controlled current source. So we'll mark controlled current source. Okay. And that is HF into II. All right. HF into II. And then we have the second component of current, which is basically H naught into V naught. Okay. So let us mark V naught location. Okay. This is V naught. V naught. Okay. So basically, H naught into V naught is nothing but current through the admittance. I'll show you how exactly you do it. So mark your admittance and write it as 1 by H naught. Okay, 1 by H naught. So the second part is basically H naught into V naught. No, what is H? Current by voltage, right? See, take it here. H is equal to current by voltage, I into V. Okay, into you're multiplying with voltage. So basically, this represents current through admittance. Okay, current through admittance. So this is the equivalent circuit of H model. Okay. So equivalent circuit, okay, of H model. Okay. So this is also a transistor model based on different approach, H model approach. Okay. So is it clear? Okay, normally it will come for 8 marks. 8 marks. Now, the simplicity of H model is that once these equations are known, then you can easily write the H models for common emitter configuration, common base configuration, as well as common collector configuration. Okay. Did you understand how to derive H parameters and how to construct the model?
Yes, sir.
Fine.
Yes.
Yes.
Yeah. Now what we will do, you see the beauty of this H model. What I will do, I will extend this H model to common emitter configuration. So I will write A as CE configuration. Okay. Now, in case of CE configuration, all what you have to do is you need to just note down what is VI and what is II, and what is V naught and what is I naught. That's all you have to note down. Okay. Now, how do you identify the input currents and the voltages? Okay. I have already drawn this symbol in the beginning also. This is base and this is collector. So this is your input current. Okay. And this is your output current. So this is your input voltage and this is your output voltage. Correct. This is your common emitter configuration. Now, what is I naught? I naught is IC. And what is II? II is the base current, IB. Okay. And what is VI? VI is voltage across base and emitter. So it is VB. Okay. Remember one thing, I'm taking small b and small e because I am dealing with AC signals. And my output voltage is seen across collector and emitter terminal. Hence, I will write output voltage as C and V. Is it understood?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. That's all. So VI is VBE, V0 is VCE, II is IB, and I0 is IC. So this is the logic you will carry forward for common base configuration as well as common collector configuration. The rest all remains the same. Fine. So let us quickly write down the performance equations. VI. So VI, right? What is VI for common emitter? It is VBE. So instead of VI, so what I will do, okay, I will give you a path also. So this, let me claim it as equation 7. Okay. So let's substitute equation 7 in equation 5 and 6. So let me write here, substitute equation 7 in equation 5 and 6. Okay. So I have my input voltage, which is VB, and then HI you have. So what I will do, I'll write HI as it is. Since I'm dealing with common emitter configuration, I will write E. So wherever you have H parameter, you are going to introduce E over there. Okay, HI becomes HIE, HF becomes HFE, so on and so forth. So it is HIE, okay, and then II. What is II? IB. Plus you have HR, and write HR, and then the output voltage, which is VCE. Then my output current is IC, which is HF into IB plus HO into VCE. As I have told you in the beginning, since we are dealing with common emitter configuration, you just introduce the second subscript. Okay, the second subscript going to be the common terminal of your configuration. So this is your H model equation for common emitter configuration. Okay, once you have the equations, you can quickly draw the circuit diagram. Okay, just you replace, in place of VI, you have VB. It's very simple. And in place of HI, you have now HIE, and this will be your base current IB. Okay, and this will be your controlled voltage source, HRE VCE. And on the output side, you have a controlled current source, dependent current source, that is HFE into IB. All right, and then you have the current flow through the admittance. You can write 1 over HOE, and this is your output voltage, VCE. You can join the two, and this will be at ground. Okay, so yeah, you can mark the current. This is your I0, okay, which is basically IC. Okay. Right, so that's your H model. So I'll write H model for CE configuration. Okay, configuration. So in exam, you may be having, you may get a question like this: build an H model for common base configuration. So what you have to do is, you have to come till equation 5 and 6, and then you have to just say that for common base configuration, what are the input currents, input voltages, and output current and output voltages. That's all. And then you just substitute and build this model. Okay, so what I will do, I will write a homework. So homework, H model for common base and common collector configuration. Okay, is it doable? You understand, right? Did you understand the C configuration model?
Yes, sir. Yes, sir.
Yes. On the same note, you can do it. Okay, just identify the input voltages and the currents. That's all. Okay. All right. Fine. Now, let me take the second topic, approximate H model. Okay. See, what happens is that this exact H model, it is simple to derive, but difficult to analyze. Okay. Let me repeat, simple to derive, but difficult to analyze. Difficult to analyze in the sense it takes a lot of time to, solve the input impedance, output impedance, the voltage gain, current gain, etc., etc. That's the reason what we do is we go for the approximation. All right. Now, a approximation is on the basis of physical observation. Okay, so when you try to find out the values of say for instance HRE, okay, HOE, or let's say this is for your common emitter configuration. Okay, and if you go for, let's say, HRB and HOB, okay, this is for common base configuration. Okay, based on the practical experimentation, the typical values of HRE is close to 2.5 into 10 to the power minus 4. Okay, on the other hand, HRB is about 3 into 10 to the power minus 4. Okay, these are the physical values obtained after conducting experiments. Okay, on the other hand, if you look at the admittance, okay, the admittance is basically it's about 1 by 40 kilo ohm, okay, for C configuration, and for CB configuration, the admittance is the reciprocal of 1 by 2 mega ohms. Okay, so if you observe these values carefully, you will come to know that these values are negligibly small, right? It is 2.5 into 10 to the power minus 4, so that's something like 0.000025, right? So you can assume this as 0. So for practical analysis sake, you can assume these are negligibly small. Okay, negligibly small. Okay, just find out reciprocal of 40 kilo. It's very small, right? It's very small. So that means to say, what you can do is, we can practically ignore HR parameter as well as HO parameter. Okay, due to their small values. Okay, so what I've done, I have given you the physical values for HRE, HRB, HOE, and HOB, right? So based on those physical values, we can take this conclusion, right? That HR and HO are negligibly small, hence they can be removed from the equation. Okay, so therefore equation 5 and 6. Okay, so what are you doing? You're basically neglecting HR, and you are also neglecting HO, right? So basically you will have equation 5 and 6 become, okay, Vi is equal to Hi into Ii, and I naught is equal to HF into V naught. Okay, let's call these two equations as, let me continue. 7, right? We have taken 8 and 9. Okay. Now, taking equation 8 and 9, we can have our equivalent circuit. So equation 8 represents KVL equation, and equation 9 represents KCL equation. So on the input side, basically we have a simple voltage source, VI, right, and a resistance HI, through which current II flows. On the other hand, on the output side, we have a simple dependent current source represented by HF into, this is I naught, right? So it's got to be I naught. II. This is II. Yeah. Correct, no? See here, I naught is equal to HF into II. Okay. Really appreciate if you had pointed out. This is HF into II. That's all. And this is your output voltage, minus plus, and the 2-port current. Okay, current. So this circuit basically represents, approximate H model. Approximate H model. And for example, if you consider CE configuration, okay, CE configuration. Say for example, I'll consider CB because I have already handled a CE configuration, right? While explaining the exact equivalent circuit. Just for a change, let me take CB configuration. If at all you have taken CB configuration, then your approximate hybrid model would have taken, these terms in it. This would have been HIV. This is your input current II. Okay, and this is your output voltage, VCB, because base is common, emitter is your input, and collector is your output. And this would have been HFB into IE. Yeah, this is your approximate H model for CB. All right, so this is your approximate hybrid model. Okay, so if, let's say, suppose you have been asked to derive an approximate hybrid model, this is how you are going to derive it. Okay, on the basis of very low values of HRE, HRB, HO, and HOB. Okay, so basically reverse voltage gain is very low and output admittance is very small. Okay, on that basis you can derive the approximate hybrid model. Did you understand this?
Yes, sir.
Okay. Last topic, let me take comparison of RE model and H model. Okay, so for the comparison's sake, what I will do, I will consider approximate. Let me consider approximate H model. So for the comparison's sake, what I will do, I will consider CE configuration. Okay, CE configuration. So what I will do, I will first, on one side, let me draw RE model in CE configuration, and on the other side, let me draw H model in CE configuration. Remember, for H model, I'm considering the approximate hybrid model. So RE model of CE configuration looks like this, right? You have beta RE and you have beta IB. Right, so this is your VI. Okay, this is your base, emitter, collector, and emitter. This is your V naught. So V naught is VCE and VI is VB, right? And this is your input current II, which is equal to IB. And this is your output current I naught, okay, which is equal to IC. So this is your RE model. Side by side, let me draw the approximate H model. Okay, so what we have is HIE, right, on the input side. And on the output side, we again have a control current source, but the definition is slightly different, right? The terminology, to be precise, it is HFE into IB. Okay, and the terms, I mean, the input and output port terminology will not change. Base is input, emitter is common, collector is output, and emitter is common. This is your output, and this is your input. Once again, this is your II, and II itself is IB. This is your I naught. This itself is your IC. Okay. Now, if you were to compare the two, okay, you would see that VI is same, which is measured across base and emitter. Here also in RE model, you will measure the input voltage across base and emitter. The only difference is the nomenclature. Okay, the difference is just the nomenclature. For beta RE in RE model, you have HIE in H model. So the similarity is that beta RE is equivalent to HIE. Okay, this is RE terminology and this is H model terminology. On the output side, you have beta IB, and for H model on the output side, you have HFE IB. So IB is common. Only beta and HFE, you have the different representations. So against beta, what we have is HFE. But beta or HFE, they both represent current gain. Okay. Similarly, whether beta RE or HIE, they both represent input impedance. So this is for CE configuration. On the other hand, if you had taken CB configuration, you would have had, instead of beta RE, you would have had alpha RE, and that alpha RE you would have compared with HIB. Okay, and alpha would have been your HFB. Okay, this is for common base configuration. On the other hand, if at all you had selected a common collector configuration, you would have had, instead of alpha RE, you would have had gamma RE, and that would have been your HIC. Okay, C for collector. And against gamma, you would have had HFC. Okay, so this is the similarity. Okay, so that's your hybrid model. Okay, that's your hybrid model. Is it, you could understand, right? Hybrid model. Okay, all right. Next up you have is performance parameters. performance parameters. Okay, so for performance parameters, okay, what we will do is, let us consider source resistance Rs as well as load resistance RL. Okay, so let's consider Rs and RL, and let us try to determine, current gain, voltage gain, input impedance, output impedance, etc., etc. Okay, so where exactly you are going to consider source and load resistance? Okay, so this is your transistor. Okay, this is on the basis of two-port network topology. So this transistor is connected to the input, right? So what we will do is, let us assume a finite source resistance. This is Vs, and this finite source resistance, let's take it as Rs. Okay, and this current, we will take it as II. Okay, and the effective voltage that is getting applied across the transistor input, we shall take it as Vi. Okay, but remember, Vi is not equal to Vs. It is, in fact, Vs is equal to Vi plus II into Rs. Okay, so what we have done is we have considered a small source resistance in series with the source. Okay, no longer we are considering it as ideal source. Okay, and on the output side, instead of taking, the no load gain, let us take a load. Okay, so let's represent that load with RL. Okay, and let us mark the voltage also. Okay, this is V naught. Okay, and let us also mark the current I naught. Okay, fine. And now we need to determine the various performance parameters, right? So let us mark the different performance parameter location. So this is Z naught, and this is your Zi, right? And let's see how exactly we do it. So what we will do is, let us replace this transistor. Okay, let us replace this black box with H model. Okay, so what I will do, I will consider exact H model, because approximation is very easy. You can neglect out HR and HF, HO terms, and you can get the approximate H model. Okay, so rest all let us retain the same. So let me quickly construct the exact H model. Okay, so we have HI, and then we have HRV naught. Okay, and on the output side, we have HF, II, and the admittance 1 by H naught. Okay, so this is your Vi minus plus, and this is your output V naught minus plus. Okay, and this is your load resistor RL. Okay, the same load we have considered, and this is your current direction I naught. Okay, and let's say this current as some I, right? Because I naught gets in, right? And it is going to split into two components, HF II component and current through this admittance. Okay, so that let us take it as some current I. And on the input side, what we have is our source, which is not ideal. Instead, it is having a finite source resistance. Okay, let's take that source resistance as Rs, and the source, let's take it as Vs. Okay, fine. So, and the input current, let's take II. Okay, so this is our exact hybrid model, right? And let us also write the H model equations. So H model equations are Vi. So Vi is equal to Hi II plus HR V naught. And then we have I naught, which is HF II plus H naught into V naught, say 1 and say 2. Okay. So what we will do, first let us find out current gain. Okay, by definition, current gain is output current to input current, right? So what do we have? We have output current as equation 2, right? Let me write it, HF II plus H naught V naught. That's my output, current equation. Let's take it as equation 2. I'm just repeating the equation 2. Okay. Now, in equation 2, we can write an expression for V naught, right? So what is V naught? V naught is the voltage across RL, right? So can I say V naught is I naught into RL? But if you look at the I naught direction, I naught is flowing from bottom to top. So it gives, voltage in flipped manner, right? So this is what we have taken, upper side positive and lower side negative. But the actual current direction of I naught gives the opposite polarity. So we can take V naught as minus I naught into RL. Okay. So let's take it as equation 3. Then just write, substitute 3 in 2. So you would get I naught is equal to HF II minus H naught into RL into I naught. Okay. Now what you can do is you can group the like terms together. You bring all I naughts onto the left hand side. So you have I naught plus I naught into H naught into RL, which is equal to HF into II. Okay. Or you can take I naught outside the bracket. So you would get 1 plus H naught into RL, which is equal to HF into II. Okay. Or you take out the ratio I naught by II, which is by definition the current gain EI, okay, which is equal to basically HF divided by 1 plus HO into RL. Okay, so that's our current gain. Okay, done. So that's our, first expression, current gain. Okay, fine. Now let's move forward. For, let's say, voltage gain, let's take up the second one. Okay, so anyhow, let me take this equation as, because we would need this equation in our future derivation as well. So equation 4, we will take it. And next up, we have the voltage gain. Okay, so by definition, voltage gain is what? Output voltage to input voltage. Okay, but we have a ready-made equation for input voltage, right? That's from the H parameter model. Vi is Hi II plus HR V naught. Okay. So what we can do is, you can substitute II from equation 4. you can substitute II from equation 4. What is it? II is equal to basically H naught into, say, cross multiplication basically. II is equal to H naught into 1 plus HORL. So let me write it is 1 plus HORL into I naught divided by HF. Okay. So substitute II from equation 4 in equation 5. Okay, so let's do that. So what do we have? We have Vi is equal to Hi into II. Against II, we have this expression 1 plus HO into RL into I naught divided by HF plus HR into V naught. Okay. Also, what you can do is you can substitute I naught as minus V naught by RL. Okay. Say 7. Say substitute 7 and 6. So what you have is Vi is equal to Hi into 1 plus H naught into RL into I naught. So in place of I naught, what we will do is we will write minus V naught divided by RL, and you have this term as well, HF, okay, plus HR into V naught. Okay. Now what you can do is, you can take V naught outside the bracket, right? Because this is common and this is common. So when you take Vi outside the bracket, you get V naught outside the bracket, you get Vi is equal to V naught times, okay, V naught times, I'm taking this in the front, this becomes HR, okay, and there is a negative sign, so this becomes negative, okay, Hi into 1 plus HO into RL, right, divided by HF into RL. HF into RL. Okay, or you can even take the LCM, taking common denominator will get you Vi is equal to V naught times, this is HR HF RL minus Hi into 1 plus HO into RL divided by HF into RL. Okay, or you take out the ratio V naught by Vi. So that ratio is defined as AV, and AV is equal to, okay, AV is equal to, you can just take the reciprocal, it is HF into RL divided by HR HF RL minus Hi 1 plus HO into RL. Okay, so that's your voltage gain. Okay, the second expression. I mean, it is easy, but just that, you have to be very careful with the substitution part. All right, so that's your second performance parameter, which is the voltage gain. Third one, let us consider the input impedance. Zi. So by definition, Zi is equal to Vi by Ii. Okay. So our aim is to take a ratio of Vi and Ii. Okay. So for that, first let us write Vi. We have readily available equation Hi Ii plus HR V naught. Okay. And we can write on, but we have V naught is equal to minus I naught into RL. So directly you can substitute. So you will have Vi is equal to Hi Ii minus HR I naught into RL. Okay. And you also have, AI as I naught by Ii. That implies I naught is equal to AI times Ii. Right? AI times Ii. That is, what is AI? AI is HF divided by 1 plus H naught into RL. In the previous step we have done. Right? So into Ii. So AI times Ii is nothing but HF into Ii divided by 1 plus HO into RL. So let's substitute, this I naught in this expression. So we get Vi is equal to Hi Ii minus HR RL, and I have my I naught. So in place of I naught, let's place this expression, that is HF into Ii divided by 1 plus HO into RL. Okay, I hope you understood the trick now. See, Ii is common, so take it out and take the ratio Vi by Ii. So that's how we are basically doing in all our derivation. So Vi is equal to Ii times Hi minus HR HF RL divided by 1 plus H naught into RL. Okay. Yeah. Or, you take out the ratio Vi by Ii. That gives Zi, and that is nothing but Hi minus HF HR RL divided by 1 plus H naught into RL. So that's our input impedance HI. Okay. If you observe carefully, Zi is basically Hi, right? Minus this. So, your exact analysis will introduce the H parameters into your ideal, equation. See, what I'm trying to tell you is that ideal Zi is Hi, but practical Zi is Hi minus, this term, this above term. Okay. So finally, we have our last hybrid parameter Z naught. Okay, Z naught. So Z naught by definition is V naught by I naught. Okay. So what we will do is that let's apply Thevenin's theorem. Okay, because the equations are slightly complex, so if possible, it's better to use Thevenin's theorem. So what we will do in Thevenin's theorem is that set source voltage Vs is equal to 0. Okay, so by setting Vs is equal to 0, okay, what you can do is you can write down first Vs expression. Okay, in the beginning I have written, right, Vs is basically Ii into Rs plus Vi. Okay, since you are setting Vs is equal to 0, LHS becomes 0, and it is Ii into Rs plus Vi, or 0 is equal to Ii into Rs plus Vi. In place of Vi, what you can do is you can write down the expression Ii Hi plus HR V naught. Okay. So just let me color it. For Vi, I have written the H parameter expression. Okay, or you can simplify to get I. So what is I? I is basically negative HR V naught, okay, divided by RS plus HI. So that is my I, which I would be needing it, okay, in the future substitution. Okay. Also, I have my output current I naught. So I naught is HFII plus H naught V naught, or I naught is equal to, okay, in place of input current, because see, to take out Z naught, I need ultimately the ratio of V by I, V naught by I naught. So I don't want this II. That's the reason I'm substituting. So what I will do, I'll write HF here, and in place of II, I have my above equation. So it is minus HR V naught divided by RS plus HI plus H naught into V naught. Okay. Take V naught outside the bracket. So you will have H naught minus HF into HR divided by RS plus HI. Okay, you can take out the LCM. So I naught is equal to V naught times H naught into RS plus HI minus HF into HR divided by RS plus HI. Okay, or take out the ratio B naught by I naught, which is equal to RS plus HI divided by H naught into RS plus HI plus HF into HR. HF into HR. Okay, so this is basically the ratio. Okay, that is your Z naught. Z naught. Okay, that is your Z naught. And if you, okay, ideal Z naught is what basically? It should be the reciprocal of the admittance, right? So if you want, I can just show you. Okay, you can just adjust the ratio. Okay, so adjusting the ratio is something like this. Okay, Z naught is equal to, what I will do, let me take RS plus HI as the common factor, both from numerator and denominator. So obviously in the numerator, you are left with unity. If at all I take out RS plus HI outside the bracket. So in the denominator, let me also take RS plus HI outside the bracket. So what do I have within the parenthesis? I have H naught and I have the ratio HF HR divided by RS plus HI. Okay, so this I can cancel out so that I can clearly show you that the exact expression for Z naught is basically, 1 over H naught and that, the second term. What is it? HF HR divided by RS plus HI. Okay, so what I'm trying to tell you over here is that if this term, okay, is very small, then you would have had your Z naught as 1 by H naught. This is basically your, ideal impedance. But due to the exact, analysis, you have the other terms coming into the picture. Okay, coming into the picture. Okay. So whatever you have calculated, AV, AI, ZI, Z naught, okay, can be extended to common emitter, common base, or common collector. All what you have to do is just substitute respective H parameters in AV, AI, ZI, Z naught expressions. All right, so only that is what you are supposed to do. In the sense, example, let me take. You had obtained, say for example, Zi as Hi minus HR RL HF divided by 1 plus H naught into RL, right? So for common base configuration, you know, this Zi becomes Hi. Since it is common base configuration, it becomes HIB minus, in place of HR, you have HRB. In place of HF, you have HFB. RL remains RL. Okay, divided by 1 plus HO becomes HOB into RL. On the other hand, for common emitter configuration, the same impedance, okay, you will have the following description. Zi becomes HIE minus HRE HFE RL divided by 1 plus HOE into RL. Okay, so this is the thing. Okay, all right. So this is about your hybrid parameter, the exact hybrid parameter circuit, the approximate hybrid parameter circuit, and the derivation of current gain, voltage gain, input and output impedances of an exact hybrid parameter circuit. All right. So in the next class, what I will do is I will solve, you know, 1 or 2 H parameter based problems. And after that, let me discuss about case study and innovative question. Okay. Any doubts?
No, sir.
No.
Yes,
Yeah. Is it too heavy? I know it is afternoon, but I had to do it. Okay, because so many holidays came in between. Okay. Take your time, go through with it. If you have any doubts, please revert. Okay. Don't hesitate. I can, you know, teach you again and again. Not a problem. All right. Fine then. So you have given the attendance, right? If you haven't given, please drop your attendance. Okay. So we'll wind up for today. Okay. Thank you.